Great. Well, we will then continue on in our discussion, which to me, like I said, is one of the most awesome things that you can do with a computer. This whole notion of having multiple programs running at the same time on a single processor, sharing this single processor, and able to operate completely independently of each other. It is like the coolest thing you can do with a computer. Okay, so we have virtualization. It's an abstraction of the processor and the memory so that each program thinks that it's the only thing running on the processor. And remember that the concept of a program as well as its execution state is called a process. So a process is a running program plus context. That's always the way that it's described in like any good OS book worth its salt. So the context is going to include all the register state, obviously. It's going to include stack state. That should also be obvious. We need the program counter. We need memory contents. We need all of this stuff so that when we switch away from the program and then we want to switch back to it, we can restore the computer's execution state exactly to where it was in the program so that we can resume where it left off. Okay, so that's the idea behind virtualization. But the thing that you'll notice is that we have all kinds of issues that we need to sort out. And that's what we're going to be doing actually for about the next 3 weeks, is looking at the various aspects of this idea and figuring out how to solve each one of the hairy little problems that we have to think about in how we would implement such an abstraction. Okay? First one. Who manages all of these problems? Remember, we had a box, and we said there's a program inside the box, and the box is, special and powerful because you can't see outside of the box. The program can run, but then somehow we have to move the program out of the box and move another program in. Who does that? So that's one thing that needs to be done. How do we interrupt a running program in order to perform a context? Remember, a context switch, if a process is a program plus context switch means we're saving the current program's context and switching to another program's context. So we have to figure out how do we get in there so that we can stop the currently running program. And then we also have to figure out who goes next. Somebody actually asked about this last time, and it's a really good question. And we're going to talk a little bit about that. And then we have the other possible circumstance, which is that the program does something bad, whether intentionally or unintentionally. Usually it's unintentional because people like to use computers to do real work. We have to make sure that that doesn't cause other programs to crash or the entire system to crash. So we have to figure out how to deal with that as well. So each process can only see its own data. Who manages the programs? And who does the context switch? So here is an idea presented for your consideration of having a separate control processor that sits and manages all of the other processes. And the control processor and the program processor are different because the control processor can see everything. It can see outside the box, it can control the box, it can control the program processor. The program processor only gets to see inside the box. Do you like this idea? You can ask yourself the question, what is the assumption underlying this approach? How much time do we expect the control processor to be doing things versus how much time we expect the program processor to be doing things? One of the things I talk a lot about in my classes is the computer is there to do useful work. What is useful work? Well, it's, maybe it's looking at cat videos. Maybe it is, writing my hum paper. Maybe it's doing a MATLAB computation. Maybe it's playing computer games. But whatever it is, it's what the user wants to be doing with the computer. If the control processor is running, are we doing useful work? Not really, right? We're switching between programs. We're doing something else. We're not doing what the user wants to do. And so if you have a well-designed system, you're going to be doing useful work most of the time, which means most of the time the control processor is going to be sitting there doing nothing, right? So does it make any sense to devote a whole bunch of silicon to having a second processor that's just there to manage the other processes? Doesn't really make sense, right? Now here's another issue. Is it possible that there might be some bugs or issues in how the control processor interacts with the various processes? Well, history says yes. What if we want to add new features to our system in how it manages programs? Well, if this is all in hardware, we're really stuck, right? We can't really extend the capabilities of this kind of system approach very easily. So this is a problem. We have a big problem with this kind of approach in that it's limited and it's wasteful. Okay, those are the issues that we have here. So separate processor implies we expect to spend a lot of time managing things. We don't want to do that. We want to be doing useful work. And also, our ability to upgrade this kind of a system design is very limited. So this is also going to make us sad. Okay? So what we're going to do instead is virtualize the control process. This is now going to be another process that is part of our computer system, and this thing's responsibility is simply to manage the other programs that are also running at the same time. Okay? But we have an interesting issue now in that we want these other programs, the text editor, the IM client, the web browser, we want those things to only do stuff with their own data and their own program. We don't want them touching each other, again, unless they both sides arrange it. But the control processor that we're now virtualizing needs to be able to do everything. So it needs to be able to handle or access all of the computer facilities that are available to it. Okay? So this is the thing. We now have two sort of modes of operation that we want the system to be able to exhibit. One mode of operation where you're stuck inside the box and you can't get out. And then you have another mode of operation where you can do everything. You can access everything. Okay? So this is actually something that's implemented in the hardware. Why have two separate processors when I can just have one processor that has two separate modes? Okay? And we call those operating modes. And it's a physical enforcement of the differences between these two sort of roles that programs can have in our computer. So we have kernel mode, which basically gives you full and complete access to the computer hardware. And you've probably also heard it called protected mode or privileged mode, but basically this is a mode of operation where you can do anything you want with the processor, so your program can do anything. Okay? Then you have user mode, which is greatly restricted. And that program has obviously limitations. It can't necessarily use every feature on the processor because if it could, then it would just switch to kernel mode and do whatever it wanted to. So user mode or normal mode has to be constrained and contained so that the program can't break out of it. Okay? So as long as we have at least these two modes in hardware, then we can implement a good operating system. Okay? I don't know, have any of you had any experience with DOS? Wow, yeah, life has changed. So, and I mean real DOS. I don't mean starting the Windows command prompt. Back in the day, like the first operating systems that we had on X86 processors, they were terrible. You could go in, and I did this a lot because it was super fun as a high schooler to tinker with this kind of thing, but you could go in and you could actually muck with the internals of the operating system. You could put yourself in between the OS and other applications and receive all of the calls that applications were making to the operating system. You could modify them. You could, prevent them from occurring successfully. You could do whatever you wanted. It was really kind of a wild time to be programming. And that got a certain stigma. People said, well, DOS isn't very good because it's allowing all of this stuff. Well, the problem is DOS was limited by the lack of support on the processor. The processor didn't have multiple operating modes. So they couldn't build a real, secure, reliable operating system. And that's why computer viruses were all over the place back then. Okay? Now that the processor, I can't remember if it was 286 or 386, where they got real protected mode, normal mode, controls so that you could actually do, have a separation of program behaviors. That's when they started building good operating systems on x86, because this abstraction was finally provided by the hardware. Okay, so yeah, the control process provides essential trusted features, so the control process is going to run in kernel mode, and the application processes will run in normal mode, or user mode. Okay. There's always this great question. What is the kernel? You guys have probably heard of kernels before, right? The kernel is just the part of the operating system that runs in kernel mode. And not that complicated a definition. But the kernel mode, the kernel is the part of the OS that runs in kernel mode. Okay, so the control process provides services to all the other processes. So this is the little starting point of building this thing called an operating system that manages the computer on behalf of other programs. Okay, that's the whole idea behind an operating system. So we have to manage the computer hardware on behalf of programs, because I mean, think about it. You've got one program that wants to access the disk and another program that wants to access the disk. Somebody's got to coordinate that. I need a chunk of memory. You need a chunk of memory. So the operating system has to manage that as well. Okay. The OS also provides this concurrent execution abstraction. One of the most powerful aspects of operating systems, so the process abstraction is how we refer to it. The OS provides a process abstraction. And then anything else that programs might want, like a file system seems like it would be a really nice thing so that we can actually store data persistently. Or talking to a network, that also seems like a nice thing that many programs would like. So a networking stack is also typically provided in an operating system and so forth. Okay, so this is sort of a nice starting point to start thinking about operating systems. All right, any questions? Okay. So this does extend our abstraction hierarchy. Remember we had, I guess at the lowest level we have the universe, right, physics, and you build up on top of that. But at least as far as we're considering, we have the computer hardware, which has the most basic facilities for executing programs. And now we're saying, besides all the stuff we've already talked about, we also need to have multiple operating modes so that we can actually build a nice, reliable, secure operating system. We have the OS itself, which governs that hardware and governs program access to it so that the programs can exist in peaceful harmony. Okay, so simple, efficient APIs for sophisticated features the programs will need. And seriously, again, I don't know if any of you have done embedded system implementation or done anything like that, but anybody who has knows that hardware is baroque and complicated, finicky, and it just generally makes life miserable. There's a saying that computer scientists have, which is that the worst thing about software is that it has to run on hardware. So, you'd like the OS to take care of all of those things and provide simple abstractions for programs to use so that they don't have to know about all those little weird details. Like the fact that on x86, for the longest time, the 1 megabyte and above, the address line was run through the keyboard controller because they didn't know how else to do it back then. That's great. So you have all kinds of weird things to deal with. So you have application programs. They are obviously designed to solve specific problems, like I need to see what my friends are doing because they're saying it on Twitter or on Instagram or whatever. I need to be able to compile my programs. I need to be able to store data, blah, 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 right? So we have applications, and then you have clients of the system, which can either be human beings or maybe it's another computer, because certainly now with the internet, you have a lot of systems that are there simply to provide services that then other programs interact with. So very common. Okay? And because you have a nice, well-implemented abstraction hierarchy, you don't have to think about all the other gory details down below unless you really want to, and then you can. And it's like we were talking about for the last week. You may be in the application program level, and you don't have to think ever about caches, hardware caches, if you don't want to. Now, it's a really good idea to, but you don't have to, because a lot of the stuff, and I can guarantee you that there's a lot of other things that you never think about, like the way that solid-state drives have to be managed and maintained to make sure that they don't get really slow, that the OS just takes care of you, for you. You don't have to think about that at all. Okay. Okay, so most processors, in fact, any real processor with like a protected mode execution now has many different operating modes that you can leverage. I say here that x86 64 provides 4 different operating modes, and that's actually not true. There's 4 operating modes that you as a potential future OS implementer may care about, but then there's even a few operating modes below those because, well, now we can run operating systems in hypervisors, so we can have multiple OSs on the same processor. See, we've extended this virtualization concept. You can even have something below the hypervisor, the system management software, and that also will run on a protected. So you might have like 6 or 7 operating modes. Okay. Also, the ARM processor, again, the kind of processor that's in most of your smartphones, has like 7 operating modes. So you have processors providing a lot of different operating modes for different circumstances. The main reason why you would want to do that is that you could come up with a lot of different categories or roles that software might need to fulfill on the system, and they don't all need equal access. So you don't need to just, like having a binary separation between user mode and kernel mode is a bit too coarse-grained for a lot of our circumstances now. Like if you think about a cell phone, you may have some software that should run when you're playing with it. You're bored on the bus or whatever, you're playing with your cell phone, and there's a certain kind of software that should run. But then if you get a phone call, you're going to switch into another operating mode, and probably the software that is running while you're in that phone call should be different. Speaking of phone calls. So, you have these different operating modes. When the phone is, it's not correct to say suspended, but when it's hibernating, it's basically not showing anything on the screen and you're not using it, it'll be in another operating mode. Certain software should be allowed to work in that mode. And then when it's, you can just go on and on and on to think about the different operating modes that a device like that could be in. And that's why there's so many different operating modes on many of these processors. Okay? So you have various roles that software falls into that would motivate having different operating modes. Okay? So yeah, we're talking specifically about desktop computers, your laptop computer that you use for general purpose computing. You could have the OS code partitioned into different chunks that take advantage of these various protection levels. Okay? And so yeah, this is x86's way of doing it, which is a little weird, but ring 0 or level 0 is the most privileged ring, at least as far as an OS implementer's perspective is concerned. Okay, like I said, there's level -1 and level -2. There may even be lower levels that, like I said, the Intel processors are pretty crazy smart by now. Level 1 and level 2 are frequently not used by x86 operating systems, and then level 3 or ring 3 is the one that you spend most of your time in, because that's where you're running your applications. Okay, and that is the least privileged level. Okay? So that's the picture. Now, now we have the ability to distinguish between the control process, which is red because it's important, and everything else, which is applications. We can put the control process into ring 0. Hooray, it can do everything. And we put everything else in ring 3, and it is limited. Okay? So we have to figure out now how we do the context switch. And we also have to figure out what do we do if a program misbehaves. You might ask yourself, why are we talking about both of these things at the same time? Well, it turns out that we've got about 3 different birds here to think about, and we're going to kill them all with one stone. Okay? So we've got to figure out, program's been running on the processor long enough, we need to stop it and get in there and pull it off and put another program on. Okay? But also we have a program that might segfault or do something else that's naughty, and so we need to make sure that we, maybe it tries to execute an instruction that's not allowed in ring 3. So we have to find out about that stuff. Okay. And you'll notice that we even have other issues that we need to solve, and we can solve them all with a single approach, which is just a very powerful approach. So we need to be able to get in there, transfer control back to the control process so that we can step in and take care of these situations. So we talked about control flow. we actually ended on that note last time. We said a program has a logical control flow, and then we said that we might have a physical control flow, which is switching between different processes running on a single processor, and that was our example of concurrency because you have overlapping logical control flows. There's another kind of control flow called exceptional control flow. And the thing is that this is different from the kind of exceptions that we talked about with programming languages in week 4. This is kind of a different beast. Okay? So let's see, yeah, so flow of control, you've got your loops, conditional subroutine calls. We talked about all of this a lot, but a lot of times you'll have interruptions that happen along the way, and you need to step in, deal with it, and then you can go back to what you were doing beforehand. Okay? And some of these examples are listed here: hardware events, timer events. Your disk says after 30 million clocks, hey, I finally got that data you asked for, and it needs to interrupt the running program to tell the operating system, hey, here's the data that so-and-so asked for. Okay, so handling the event, you have to jump to a very different location. A lot of times you're actually leaving the application and going to the control program or the kernel, and so we call this exceptional control flow. And there are, you can think of it as being 2 major categories of exceptional control flow. One is if hardware wants our attention, and the other is, wait for it, when software wants our attention. So we're looking at it from the perspective of the kernel. Hardware says, hey, I need some help. Software says, hey, I want some attention. Okay? So we have interrupts, which are sort of the general hardware exceptional control flow category. Okay? So an I/O device that says it's ready to do something, and it's typically not caused at all by executing an instruction. That's kind of the big point here, is that interrupts tend to be not caused by an instruction. And then you have exceptions, which are generated by software. So an instruction will execute, and that causes something to happen. Maybe you have a move instruction that tries to dereference an invalid address. Again, everybody in this room has done that. And now the operating system says, okay, program, you need some attention. Okay? Also, you can have intentional exceptions, and that's kind of an interesting circumstance. We'll talk about why you want to do that in a moment. And so these are the 2 general categories. And like I was saying before, this is different from your programming language exceptions because a lot of times in programming languages, when an exception occurs, you're saying this computation can't be completed. It can't be performed. And so you leave the computation and you go to an error handler. Okay? So that's not the way that hardware exception handling works. Typically what happens in these cases is you handle the exception and then you go back to what you were doing. Now, you may not go back to it right away, because if you have a program that says, I want to read data from the disk, and now that program has to wait for 30 million clocks, or 20 million clocks, or whatever, well, the best thing to do to that program is to say, okay, context switch away from the program. And now we're going to context switch to another program, and that program will start to run. Okay? So now we've switched away from that program, but eventually the data will be loaded, and the disk controller will say, I got data. It'll fire an interrupt, and the operating system will get the data into memory, and then it'll switch back to that program. So it may be that a lot of other things happen in between, but eventually we get back to the interrupted part of the program. Okay? So we have these categories, if you will, of exceptions. And I don't want you to be confused by the previous slide, which had interrupts and exceptions. That slide is true, but it's talking at a very coarse level of granularity. This is a much more fine-grained picture. In fact, we have interrupts, which are kind of the same thing. They're generated by hardware. And then we have traps, faults, and aborts. And some of those things are caused by hardware, and some of them are caused by software. Okay, traps and faults in particular are always caused by software. And then aborts can be caused by hardware, hardware saying, hey, I think you shouldn't use me anymore. That's the idea behind an abort. Okay? So just be aware that this is a finer grain assessment of sources of errors or types of exceptions, and the previous slide was a very coarse-grained, high-level view. Okay, so we have interrupts caused by hardware. such as a periodic timer. So x86 and many other processors have hardware timers that you can configure. You know, you can say start at this number and count down at this rate, and when it hits 0, bang, it fires off an interrupt. Okay? So this is really useful because we could actually use that to say this program has a certain amount of time on the processor. We'll start the timer, and the timer will count down, and when the timer goes off, an interrupt fires, the control process gets informed, and it context switches away from that program. So this is a nice, simple way that we can build a context switch mechanism. And of course, these timers, as you can guess, are not able to be configured by user programs, because if they were, then the user program would just say, well, I want forever. I want infinite amount of time. Never fire the interrupt. And then it gets the processor. So since that would be bad, the hardware timers are protected. They can only be configured from protected mode. Then you have traps. These are intentional exceptions caused by programs. Okay? If you have an application that's running in a reduced set of capabilities, because it's running in user mode, and it wants to talk to hardware and it can't do it directly, what's its only recourse? Well, it's got to ask the operating system for help, right? So it can cause a trap that will inform the operating system that it needs attention. Okay, so this is very often used for operating system calls. The caller, the application, will say what it wants done, and then the processor will switch from user mode to protected mode. So we'll go into the kernel, and the kernel will do its thing. Okay, it'll take care of the request on behalf of the program. Okay, and like I said, depending on the request, if the request is nice and simple, like I need my heap size to grow because my malloc has come back and said that I've used up all my heap space, and the program wants to extend the size of its heap, then the OS can come back right away. If it's read a disk, then it may come back a lot later. Okay, then you have faults. Faults are unintentional. So you can think of it as like you're walking along and then all of a sudden you run into a circumstance that you didn't know would occur, but it's something that you can't resolve. Okay? That's a fault. So you have your program executing along, it runs an instruction, and that instruction causes some kind of error that may be recoverable. Okay, that's the thing that's really neat about this, is that it may actually be recoverable. Now we're going to, in typical Caltech style, we're going to jump ahead briefly to talk about something that we haven't actually discussed in this class yet. But there's this notion of swap space. Probably all of you have seen and are aware that your computer has some swap storage that's on your disk, so that it can actually have data that is not in memory, so it can free up available memory for programs to use and save some of that data to disk. Okay? And so this is called a virtual memory abstraction. We're going to talk about it a lot in a couple of lectures. So if you have a program executing and it accesses an address, that the address is not currently a valid address for that program, it causes a fault. The operating system kernel finds out by a fault being triggered. And so it will have a fault handler, and it can go in and look at, well, what address was accessed? Because the OS knows everything. I mean, it's running in protected mode. It can see everything. So it is informed what address was accessed. It's informed what kind of fault it was. Is it just a page fault where you access an invalid address, or is it a protection fault because you're trying to write to read-only memory or execute something that's not executable? So it gets all that information. Okay. And then the handler can say, oh, this is a page that was actually swapped out to disk. So I'll just load that data from disk into the appropriate location in memory. And so that's all happening. The program is suspended right now, so that's all happening behind the scenes. And what happens is, when the OS returns to that program, it goes back to the very instruction that caused the fault. Because why not? I mean, that was the instruction that couldn't be executed, so let's try it again. That's the whole idea behind a fault, is that the instruction couldn't be executed. Let's go resolve the situation and go back and try the instruction again, and now it will work. Okay? And like I say here, now the instruction will presumably succeed. That is, if the OS is written properly. Okay? It's certainly possible for the OS to think the fault was resolved, and it's not really resolved. So you go back to the program, execute the instruction again, and it faults again. Okay, that happens a lot in 124. It's always fun. I mean, not at the time, but it's fun later. So to look back on and laugh. So you may have a situation, though, where the fault handler says, there's no way for me to resolve this. Think about if you wrote the world's simplest program. You know, void star p equals null star p. Right? We all know what that program's going to do. It's going to crash. Okay? Well, that's also generating a page fault, but the OS gets informed and it looks at the address that was accessed and it said, 0 is not a valid address in this program's address space. I'm going to kill the program. Okay? So this is all handled through the faulting mechanism that the processor provides, and the OS figures out what to do based on this specific kind of fault. Okay, any questions about that? Good, because we're going to talk a whole lot more about it. These are some of the last lectures that we'll have in this class, and you'll see how all of it works. And you'll start to realize all the amazing things that your computer is doing when you write that program that crashes. I mean, it actually is really quite amazingly sophisticated. Okay, and then you have your aborts, which are always sadness, because when you have an abort, it means that your computer hardware is giving up. It's saying, I ran into something and I don't trust my brain anymore, so I'm going to stop. And aborts are non-recoverable. Typically what you have to do is hard reset the system because anything else is a bad idea. You can't really trust the computational machinery any longer. Okay? Yes?
How would something like running out of battery or something overheat, or would it not be handled by this?
Running out of battery is an interesting one. I'm trying to think how that would... I don't know that that would actually be a hardware type issue. I think typically the way that's implemented on most computers nowadays, I'm not saying it will always and forever be that way, I'm just thinking of how it's done right now. I think it's something where software monitors that and then decides what to do, but while it still has enough power to do something. Because I think we've all run our computers to the point that they just turn off. You know, you can do the same thing by holding your power button down. Okay? When you push your power button, that actually will cause an interrupt, and your operating system can respond to it if it wants to. Like if I hit the power button right now, which would be a bad idea in the middle of lecture, but if I hit the power button right now, my computer, I am hoping, would cleanly shut down. But if I hold the button down for like 4 seconds, then it just turns off. That's not a software behavior, that's a hardware behavior. And it doesn't really involve interrupts. Okay? So things like power management, I think, are more software driven. What was your other?
If something overheats.
Yeah, overheating. That is an interesting question as well. I know that there's software mechanisms for monitoring temperatures on the motherboard and on the processor. I don't remember if there's a hardware interrupt for it. That's something that I'd have to go look up. I'm not sure. Yeah. Any other questions or comments? Yeah, I mean, what you'll notice is that the set of interrupts that the processor understands is actually very basic, pretty limited. And then a lot of sophistication is built on top of it in software. Okay? All right, but this would be like your parity errors. You know, if you actually have memory with parity bits, and it says, oh, this bit flipped, and the parity doesn't add up any longer. Oh, man, okay, I better stop. Things like that. Let's see, yeah, so you may have the whole system. This is a cause of blue screens of death. It's not the only one, but certainly that is one way to get there. Your computer just quits. Okay. Let's see, yeah, so this is what I was talking about before. X86 processors have 256 different kinds of exceptions, and so they're labeled 0 to 255. That's not really shocking there. We're going to talk a little bit about how this all works at a level that is a bit more detailed than you really need to know. But I want to illustrate the mechanism and how it is engineered. It actually becomes much more important in 124, where we spend more time on it. So 0 to 31, hard-coded hardware exceptions and interrupts. These are things like, you know, your timer interrupt goes off, or you decided to execute an illegal instruction, or You divide it by 0, something silly like that. Okay, there's a few things, or you try to access null. Okay, so those are all hardware-defined interrupts. Yeah, so these are just a few examples. Exception 13, general protection fault. So that would be something that gets triggered when you try to access memory badly. Okay, and then exception 18 is the machine check abort. Okay, and so these are things that you don't really have a whole lot of control over. They just are there, and obviously any good operating system is going to provide handlers for all of these things so that it can find out that stuff is happening. Now 32 through 255, these are the configurable ones. It turns out that the OS is going to register a handler for every single one of these. Not every single one of them will be meaningful though. Some of them it will just register a handler for, so that if somebody decides to be silly and use interrupt whatever, then it'll know about it, and it can go ahead and tell that program to knock it off. Okay? But typically what you'll see is one of those interrupts will be devoted to getting into the kernel. So this is how you trap into the kernel to ask it to do things for you. Okay? So on Unix it would be hex 80. Windows I think is 2E. It used to be int 20 in DOS days. You know, this stuff was all specified so that programs could access system facilities in some clean way. Okay, but there's no reason to pick one over another. Like in Pintos, we pick interrupt 30, just because that's the way Pintos was implemented for CS124. Okay, you can invoke the handler for any type of exception if you would like. I'm not sure what the behavior is. For example, if you invoke a hardware interrupt, that would probably be bad, and hopefully the processor will stop you. But you just say int n. Whatever n is, that's going to be a number, and then it invokes the appropriate exception. I don't believe that n can be a register. I think it has to be an immediate value. Okay. Now, let's say that a piece of hardware says I want attention, or let's say that a piece of software does something and needs attention. Well, in that case, you have to dispatch to the appropriate interrupt handler. And so this is handled through this special table on X86. It's called the interrupt descriptor table. The interrupt descriptor table is an array of 256 entries, because we have 256 interrupts, and each entry says what to do when that interrupt occurs. That's all the interrupt descriptor table does. Now again, if you come from an embedded systems background, maybe X86 or 186 programming, then you may be familiar with the interrupt vector table. That's the real mode version of this. This is the protected mode version. Okay? So even on the single Intel 64-bit X86 processor, it'll use different names depending on the operating mode. So interrupt descriptor table, 256 entries. Each one is 16 bytes. And you can actually point the processor at what interrupt descriptor table it should use. Guess what? One of the first things that an operating system does when it's bootstrapping, it installs an interrupt descriptor table so that when interrupts happen, the processor can inform the OS, and the OS can handle it. So you can see that there are instructions here. Those are obviously protected mode instructions because you don't want applications going in and tinkering with this. Okay. So an exception n, just one sec, when exception n occurs, then it's a very straightforward array indexing mechanism. Take n, multiply it by 16, add in the interrupt descriptor table register, that's your entry, and then the processor's machinery pulls those 16 bytes and figures out what to do based on those bytes. Part of it is an address to jump to so that it can invoke the handler. Okay, question?
So where is this stored in the hardware?
Where is it stored in the hardware? This is going to be in your main memory somewhere. Yeah, so your DRAM memory is going to have this table stored in it, which has some interesting implications that we'll talk about when we get to virtual memory. Yeah?
Seeing that your OS has to pick some strategy of transferring arguments and stuff to the kernel.
Yes, there does have to be some strategy for transferring arguments. Everybody see that? We need a convention again. And different operating system implementations will have different conventions. You're not really constrained. I mean, there's no like one right way to do this. And so most of the time, when operating systems provide a trap handler so that you can make system calls, they'll pass arguments in registers. Because we have a lot of them, and that's easy, and it's fast. And we don't have to worry about stacks. You'll see why not worrying about stacks is actually really desirable in a sec. But Yeah. Again, for CS124 and Pintos, they're passed on the stack, just so that you can think about it. It's terrible. It's actually not the way that people normally do it, and it's complicated, and you see why people don't do it that way. But yeah, again, you have to have a convention for how arguments are going to be passed to the operating system. Okay. Any other questions? Okay, so interrupt descriptor record encodes call address and privilege information, and we call it a gate descriptor. And there's a very important reason why. We have call gates. Okay, so that's if I want to make a call. The whole point of having a gate is that we're changing from one protection level to another protection level. We want to control this operation. We don't want to allow it at just any time or from any address to any address, because then we have chaos. We don't have sanity in this world. So we have call gates, interrupt gates, /trap gates, and task gates. Really, the only one we care about is that middle one, interrupt gates. Those are the ones that are used all the time. Because think about it. I'm running in my program, and then the disk controller says I have data. Well, we need to get into the kernel, so somehow the disk controller interrupt needs to cause the processor to go from running my program in ring 3 to the operating system kernel in ring 0. So we're changing protection levels. That needs to be carefully orchestrated. And all of these gates function, yeah. In fact, one of the students who's been a TA for this class sent me a message a day or two ago about a new issue that we have. Some of you may have noticed this issue. There's a special way you can tell the processor to do debugging, and debugging is actually supported at the hardware level. Maybe some of you are familiar with this, but when you single-step debug your program, the debugger puts the processor into a special mode where after every instruction is executed, it fires an interrupt, so that the debugger can step in and say, here's the state of your registers, here's the state of this and that. So you take another step, and then another interrupt is fired after the instruction executes. Well, it turns out that you can abuse this mechanism to tell the processor to fire a debug interrupt once you've entered into the kernel. And now you can start getting information out of the kernel. It's like pretty poorly engineered. So fortunately, the fix is on the way, so this is something that has already been fixed. But you can see how easily, if you can circumvent the machinery for transitioning between different protection rings, you can wreak havoc. Have all kinds of problems. So why are they called gates? Because we have this privilege ring model, and gates are the way that we get between protection levels. It's like a castle. Okay? So we move between these, and we need to have very careful control over how we move between these gates. All right? So basically that allows us to manage privilege levels. Let's see what I say here. So interrupt, fault, and abort handlers. What's special about these? The application didn't request it, hardware requested it, or it just happened. Okay? So if the handler needs to use privileged instructions, then you go to the higher privilege level. Easy peasy, that's all you do. Okay? Since the program was interrupted, they can't really affect the handler. Trap handlers are the ones where the user application actually intentionally did this, so it's trapping into the operating system kernel. You can start out at the lower privilege level and make sure everything is sane and then go straight to the higher privilege level. Okay? Or, if you're really trusting yourself, you can go straight to the higher privilege level, do your checks there, and then you can go back, or you can kill the program, or you can do whatever you need. Okay? So depending on the way the OS is constructed, you can solve this problem in various ways. Okay? Now, I've mentioned before that most of the time OSs are really just going to use ring 0 and ring 3, like if we're talking X86. Other processors obviously will have different rings, but they'll do similar things. So the OS will use ring 3 and ring 0. And so the application might say, hey, I'd like to change my user password. So it sets up the call and asks the operating system kernel nicely. It says, hey, can I change my password? And so you have a trap handler that goes into ring 0, verifies the request, and then performs the operation. Okay? if you have a situation where a virtual machine is running, you know, all of you are doing that this term. I should say all of you because some of you are still using like Linux natively on your hardware, and that's fine. But if you're running in a virtual machine, then sometimes that virtual machine operating system needs to ask the host operating system for stuff. And so it has its own special interrupts that it can use to ask the host OS, hey, can you help me out here? I need some help with something. Okay? So that tends to be the way that it works. Now, these handlers need to be well implemented, carefully implemented. There was, I mean, you always hear about these stories. Probably 10 years ago, 12 years ago, when I was just getting started teaching, an exploit came out where a very widely used, important system call was implemented incorrectly. It had a bug in the code, and you could run a little program that would invoke the system call in a special way, and suddenly you had root privileges. Okay, that's no good, right? Apple had one like maybe 3 or 4 years ago where they had code that had like double return, or they had an if without curly braces around it or something, and just a bug. But when it's in the trap handler, it's really serious because now somebody can figure it out and take advantage of it. So you have privilege escalation exploits. Nobody wants that. Okay? So yeah, if you have buffer overflow issues in your OS, then you're sad. Okay, you're going to be very sad. In fact, if you have an OS, if you think about it, the user mode application could say, hey, I'd really love you to access this address. Give me the data at this address. And if the OS just trusted that address, then the application could give it addresses in the kernel. And the kernel can do everything. So it'd be like, sure, here you go. Here's your data. Oh, wait, that's my data. And then we're sad. Okay? So the OS kernel really has to verify everything that comes from the user application. We're going to talk about that more in the future. Okay, so yeah, we have just a few more minutes, so I'll try to get through the important parts of this, and you can study the rest on your own. X86 64 has this quality that is quite appealing, which is that every protection level has its own stack. If you think of a user application, how could it be misbehaved and so forth? Well, if it's mangled up its stack and it makes a call into the OS kernel, we don't want that affecting us. If the user application has used up most of its stack and so there's hardly any space left, we don't want that to affect the OS. And so the OS in a different protection level has its own stack. Okay? This is what makes it hard to pass arguments by stack, because when we switch protection rings, we actually switch stacks as well. Okay? That's why it's annoying to do this protection level switch and pass arguments. So typically arguments are passed in registers because that's just simpler. Okay? So here I'm going to give you a whirlwind tour. Okay? Interrupt handling works a lot like, and we're talking exceptions now, so software-generated exceptions works very much like a call, except we have other things that can happen along the way. We have to save the flags register because we may be interrupting in between two parts of a comparison. Okay. We save the return address onto the stack. That goes without saying. Yeah, so this is just to spell this out. I think everybody understands it. If you had an interrupt between a comparison and a conditional jump, you need to be able to come back and finish that. So that's why the flags register is saved. Okay. So blah, blah, blah. So application, let me see what I say here. Yeah, so hardware interrupt occurs. Oh yeah, so this is another thing that's really interesting is that you can have a hardware interrupt occur, and then if the handler takes a long time, you could have another one of the same interrupt occur again. That would be bad. And so we have a special flag in the flags register that controls whether or not interrupts can be delivered. Okay, it's called the interrupt flag. And so when it's on, interrupts can be delivered. But if you set it to 0, then the maskable hardware interrupts can no longer be delivered. They're told to wait, basically. They'll be queued, they'll be pending, but they won't actually be delivered. And so basically what happens is when the hardware interrupt occurs and you go into the kernel, you save the flags register and the interrupt flag is cleared. The version of the flags that is saved still has that interrupt flag set. Okay? That way hardware interrupts cannot interrupt themselves because that would be bad. Okay? So yeah, like I say here, the interrupt exception operator. Oh yeah, of course, because if you're running in the kernel, it's going to be doing comparisons as well. That's going to affect the flags register. You're going to have carry flags and sign flags and all kinds of things going on. So when we go back to the interrupted code, we need that flags register to be back the way it was so that the interrupted code can actually see everything looking the way it got interrupted from. Okay? And like I say here on the bullet point, it also automatically re-enables interrupts for us. Okay, yeah, so traps don't automatically disable interrupts, and then there's a special kind of interrupt that can't be masked, and this is for like your emergencies. The NMI, it's the bat signal for the processor. Okay, so if hardware is like, I cannot be ignored, I must not be ignored, then it can use a non-maskable interrupt instead. Okay. I know we're glossing over a lot of this. I just want to expose you to these details. They don't become as critical until we get into operating system implementation. Okay, so we have these stacks, and so the exceptional control flow may change what stack is being used. So basically what happens is if you're changing protection levels, the new stack gets information about the stack that we're switching from so that we can restore it when we go back. Okay? If you're switching, if you have a ring 3 operation and you go to ring 3, I'm sorry, I should say this more accurately. You're going from ring 0 to ring 0 because you're in the kernel servicing a trap and then a hardware interrupt occurs. You don't switch stacks. You're already in the ring 0 stack. Okay, but if you're changing protection levels, then it will change stack. Save the caller return address, save our flags onto the stack. And so basically, that's everything that's necessary to go back to what was interrupted. Okay. So going back, you can see that int does a lot of work. So there's a special instruction called iret, which undoes all of that stuff. It basically does the reverse order of all of those things. So restore flags, restore the instruction pointer from the stack, and if we're going back to another protection level, then it also changes the stack back to the stack that was interrupted from. Okay? Everybody got that? Again, this is a high-level description. I don't want you to get lost in if you're like, Donnie, this is overload. Yeah, well, I understand. You don't really have to know all these details really precisely, but I do want you to understand the things that happen when you trap into the kernel or a hardware interrupt goes off, because it will become relevant. Okay, so let's just throw this up here. We needed a way for the control process to find out when bad things happen and a way to get it onto the processor when a program runs out of time or so forth. So context switches, we just have a timer interrupt handler that does the context switching for us. Okay, so we can do that. Blah, blah, blah. And when a process misbehaves, we'll get a fault or something like that, and then the control process will be informed and it can go ahead and do the right thing. Okay, so a process causes a general protection fault, the control process is invoked, it can terminate the process, and then it can switch to someone else who hasn't misbehaved yet. You know, let's say it that way. Okay, so basically, once we have all this, we can actually build a major chunk of our virtual process abstraction. Okay, everybody got that? Any questions? All right, there are a few more slides, but they're summary slides, so you can read those on their own. They're sort of like, rah, rah, look how cool we are, we've accomplished things. But we're going to go ahead and leave off here, and we'll pick up this discussion next time.